The world we live in is full of patterns. Day and night, the seasons, and the movement of animals. Even before humans knew mathematics, the world itself was already performing it. But at some point, humans decided not just to watch the world, but to understand it. Why mathematics began. So why did mathematics begin in the first place? Mathematics did not begin with formulas. It began with a need. The need to understand patterns. Even animals seem to have a basic sense of mathematics. They can estimate distance. They can tell whether their group is small or large. They decide whether to attack or retreat. All of this means that, at its earliest level, mathematics was connected to survival. But humans went one step further. They began to count, measure, and bring order to the world around them. Ancient Egypt. Where mathematics became serious Egypt is where mathematics became serious. Our story begins beside the Nile around 3,600 years ago, when Egypt was one of the most advanced civilizations in the world, and the pharaohs ruled the land. The Egyptians realized that the Nile flooded every year. These floods made their farmland more fertile, but they also erased the boundaries between fields. That meant people had to work out year after year where their land began and ended and exactly how large it was. This was the moment mathematics suddenly became serious. It was no longer just about curiosity. It was about real life. They had to calculate the area of a field, estimate how much food it would produce, and determine how much tax should be paid. What is especially interesting is that their measuring tools were based on the human body. The width of a palm became a unit of measurement, and the distance from the elbow to the tip of the middle finger became the cubit. In other words, the human body became one of the first rulers in history. Mathematics and bureaucracy. Mathematics became closely connected to bureaucracy. The important point is that mathematics helped people administer an entire society. If your field was smaller, you should pay less tax. If your field was larger, you should pay more. So everything had to be calculated carefully. The Egyptian number system was both interesting and inconvenient. The Egyptian number system. In one important way, their system was similar to the number system we use today. It was a base 10, or decimal system, but it had one major difference. Something we barely even think about today. The Egyptians did not have place value. What does that mean? It means that a symbol for 1 always represented 1. Its value could not change to 10 or 100 depending on its position. So, when they wanted to write large numbers, they had to repeat many symbols. Even so, their methods for solving problems were remarkable. The Rhind Papyrus, one of the earliest mathematics texts. The Rhind mathematical papyrus is one of the most important surviving mathematical documents from ancient Egypt. It contains practical problems and methods for multiplication and division, including questions about sharing food among groups of people, Egyptian multiplication, and binary thinking. Let me show you one of their strange but brilliant multiplication methods. Suppose they wanted to multiply 3 by 6. They repeatedly doubled the number. 3, 3, 6, 12. In the other column, they wrote powers of 2. 1, 2, 4. Next, they asked, how can we build the number 6 using 1, 2, and 4? That is easy. 2 plus 4 equals 6. So they selected the rows corresponding to 2 and 4, then added the matching values, 6 and 12. The result was 18, so 3 multiplied by 6 equals 18. You might be wondering what is so special about this. The Egyptians were decomposing numbers into powers of 2, an idea closely related to binary representation. It is not that modern computers directly came from this Egyptian technique, but the underlying logic is surprisingly similar to the binary thinking used in digital technology thousands of years later. The bread problem and the development of fractions. One ancient Egyptian text contains an interesting question often described as a bread-sharing problem. Imagine that you have 9 loaves of bread and 10 people. How can you divide the bread fairly so that everyone receives the same amount? Each person must receive 9/10 of a loaf. The Egyptians often expressed fractions as sums of distinct unit fractions, so 9/10 could be written as 1/2 plus 1/3 plus 1/15. One possible process would begin by dividing 5 loaves into halves, so each person receives 1/2. The remaining 4 loaves could then be divided into smaller fractional parts until everyone receives the same total amount. Why is this important? Because it shows how fractions became essential tools for solving real problems. The Eye of Horus and geometric series. Now, let's look at another famous Egyptian idea, the fractions associated with the Eye of Horus. Different parts of the eye were linked to fractions such as 1/2, 1/4, 1/8, and so on. These fractions follow the pattern of a geometric series. If the pattern continues forever, the total gets closer and closer to 1 without exceeding it. The traditional 6 Eye of Horus fractions themselves add up to 63/64. Circles and pi in ancient Egypt. Now, let's talk about circles and the number pi. The Egyptians wanted to estimate the area of a circular field, but they did not know our modern area formula, and they did not use pi as a named constant. So they transformed the circle into a shape they understood better, a square. For example, if a circle had a diameter of 9 units, they subtracted 1/9 of the diameter. That gave them 8. Then they said that the circle's area was approximately equal to the area of a square with side length 8. So the estimated area was 64 square units. According to modern mathematics, if the diameter is 9, the radius is 4.5, and the area is pi multiplied by 4.5 squared. If we set the Egyptian estimate, 64, approximately equal to pi times 4.5 squared, we get an implied value of pi of about 3.16. That is remarkably close to the true value. The pyramids. A living display of mathematics. The Egyptian pyramids are not just buildings. They are living displays of mathematics. They are filled with symmetry. Viewed from above, the 4 sides of a square pyramid form a carefully balanced structure. Their geometry is astonishingly precise. The angles, lengths, slopes, and alignments were all planned with great care. Some popular theories claim that the Great Pyramid contains a ratio close to the Golden Ratio, particularly in the relationship between its slant geometry, its height, and half the length of its base. Whether this was intentional is still debated, but the mathematics of the pyramids is such a huge subject that it deserves an entire video of its own. The 3 to 4, 5 triangle before Pythagoras. The 3, 4, 5 triangle existed long before Pythagoras. Ancient builders knew that a triangle with side lengths 3, 4, and 5 forms a right angle. They could use this practical fact even without knowing the theorem in the formal form we associate with Pythagoras today. The first steps toward calculus. We can even find early ideas that point toward calculus. One Egyptian papyrus contains a correct formula for the volume of a truncated pyramid, also called a frustum. What matters is not only the formula itself, but the kind of thinking behind it. Breaking a shape into more manageable pieces, making approximations, and gradually moving toward an accurate result. Ideas like these would, thousands of years later, become central to what we now call calculus. What ancient Egypt gave to mathematics. So far, we can say that one of the earliest places where mathematics developed in a systematic and serious way was ancient Egypt, beside the Nile, around 600 years ago. The Egyptians achieved extraordinary things in counting, measurement, geometry, approximation, and even in ideas that can be seen as distant ancestors of calculus. But their mathematics mainly dealt with specific numerical problems. It did not yet emphasize general proof or abstract generalization. Then another civilization entered the story and took the power of numbers to a completely different level. Babylon. When numbers became more powerful, the Egyptians measured the world, but something was still missing. Numbers had not yet revealed their full power. Then another civilization appeared, one that did not merely play with numbers, but used them to organize society, trade, astronomy, and government. We now enter Babylon in ancient Mesopotamia around 1800 BCE, in a region that largely corresponds to modern-day Iraq and parts of the surrounding Middle East. One of the greatest differences between the Babylonians and the Egyptians was their remarkable number system, the base 60 number system. The Babylonian number system was very different from ours. The system we use is decimal, which means it is based on 10. The Babylonian system was based on 60. But why 60? Because 60 is an incredibly useful number. It can be divided evenly in many different ways. It is divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, which makes it extremely convenient for working with fractions. We still use traces of base 60 today. 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. Place value. Babylon's big leap. The Babylonians also made a major advance that the Egyptians did not have: place value. Place value means that the position of a symbol changes its value. The Egyptians had to repeat many symbols when writing large numbers. The Babylonians had a simpler and much more powerful idea. Instead of constantly inventing or repeating symbols, they could change the position of the same symbols. A symbol in one position could represent 1. In the next position, it could represent 60. And in the following position, it could represent 60 squared, or 3,600. Why was this important? Because it allowed people to write very large numbers using only a small number of symbols. This idea became one of the foundations of modern numerical notation. The birth of zero. The Babylonians also realized that an empty position could carry meaning. So they eventually used a placeholder symbol to mark an empty place. It was not yet zero as a full number in the modern sense, but it was an important step toward the concept of zero. Equations. The first step toward algebra. The Babylonians also solved problems that we would now describe using equations. Their problems were often practical. For example, finding an unknown length from the area of a field. Imagine a rectangle with an area of 55 square units, where one side is 6 units longer than the other. What is the length of the shorter side? Instead of writing a symbolic formula, the Babylonians solved the problem geometrically. They cut and rearranged parts of the figure until the problem became a square. Using a method closely related to what we now call completing the square, they obtained the answer. The shorter side is 5, and the longer side is 11. Triangles before Pythagoras. The Babylonians also understood right triangles long before Pythagoras. A famous clay tablet known as Plimpton 322 contains lists of numbers, but these are not random numbers. They are related to sets of side lengths that form right triangles. In such a triangle, the sum of the squares of the two shorter sides equals the square of the longest side. That is exactly the relationship we now call the Pythagorean theorem. Yet Plimpton 322 was created more than 1,000 years before Pythagoras. The strange number 2. The Babylonians did not work only with simple whole numbers. They also encountered a strange number, the square root of 2. They calculated an extraordinarily accurate approximation of it, about 1.41423. I will not explain their exact method here because it would take us too far from the main story. But there was one major difference between their mathematics and modern mathematics. They could calculate the answer, but they did not build a formal proof explaining why the result had to be true. So, the Babylonians had learned to control numbers. They calculated with them, solved problems with them, and used them to make predictions. But one crucial question remained. Why is the answer correct? Their mathematical tradition was not primarily built to answer that question. And then a true revolution began. Greece, the revolution of proof. The Babylonians knew how to find answers, but one important question was still waiting. Why is this answer true? That question takes us to ancient Greece. This was the great change. Mathematics began to move from simply solving problems to understanding them. Greek mathematicians did not only want an answer, they wanted a proof. Pythagoras in the beginning of the story. The name Pythagoras is familiar to almost everyone. The theorem associated with him says that in a right triangle, the sum of the squares of the two shorter sides equals the square of the hypotenuse. But the important point is not that Pythagoras was the first person ever to know this numerical relationship. As we have already seen, Egyptians and Babylonians had used related ideas much earlier. What became central in the Greek tradition was proof, showing logically why the relationship must always be true. Today, hundreds of different proofs of the Pythagorean theorem are known. More than 370 have been collected, and new variations continue to appear. The shock of irrational numbers. The Pythagorean theorem also created a major problem: irrational numbers. If we draw a square with side length 1, its diagonal has length square root of 2. This number cannot be written as a ratio of two whole numbers, and its decimal expansion never terminates or repeats. It is irrational. Why did that matter so much? The Pythagoreans believed that everything in the universe could be explained through simple ratios, but this number refused to fit that belief. According to later stories, the discovery was kept secret within the Pythagorean community because it seemed to threaten their idea of a perfectly ordered universe. Its real mathematical importance was that it forced Greek thinkers to rebuild mathematics on firmer foundations, not only through numbers but through geometry and logic. Plato and the importance of geometry. Plato founded a school called the Academy. A famous later tradition claims that an inscription at its entrance said, "Let no one ignorant of geometry enter here." For Greek thinkers, geometry had become a path toward understanding the structure of the world. Plato was not a mathematician in the same sense as Euclid or Archimedes, but he helped transform mathematics from a practical tool into a disciplined way of thinking. Euclid and the structure of mathematics. Euclid gave mathematics a structure. He collected and organized much of the mathematical knowledge available in his time in a work called The Elements. The central idea was to begin with a small number of definitions, common notions, and postulates, and then use logical reasoning to derive new results from them. That is essentially what we still do when we prove theorems, and it became a foundation of modern mathematics. At this point, mathematics became a logical system, not merely a practical tool. Pythagoras and music. There is also a famous story connecting Pythagorean ideas, music, and numbers. Pleasant musical intervals can be related to simple numerical ratios. Imagine a vibrating string on a musical instrument. If you play the entire string, you hear one note. Now shorten the vibrating length to 1/2 of the original string. The sound is higher, but it feels closely related to the first note. This interval is called an octave. Other simple ratios, such as 2/3 or 3/4 of the string length, also produce harmonious intervals. But when the lengths are related by more complicated ratios, the notes may no longer create the same sense of consonance, and our ears perceive greater tension or dissonance. Even music has mathematics inside it. Archimedes and approaching infinity. Archimedes was far ahead of his time. One of his problems was this: how can we calculate the area of a circle with greater precision, rather than relying on a rough approximation? He compared the circle with shapes he could calculate, drawing polygons inside and outside it. He began with a hexagon and repeatedly doubled the number of sides: 6, 12, 24, 48, and finally 96. As the number of sides increased, the polygons became more and more like the circle. There is a profound idea here. By approaching a value step by step, we can trap it between increasingly accurate bounds. This way of thinking later became central to the concept of limits, and limits became one of the foundations of calculus. The Death of Archimedes. The Death of Archimedes is also surrounded by a famous story. When Roman soldiers entered Syracuse, Archimedes was said to be absorbed in a mathematical diagram. According to tradition, when a soldier approached him, Archimedes said something like, "Do not disturb my circles." The soldier killed him, even though the Roman commander Marcellus had reportedly wanted Archimedes captured alive. Hypatia, the end of an era. Several centuries later, in the city of Alexandria, the Greek mathematical tradition was still alive, and one of the people keeping it alive was a woman named Hypatia. Hypatia was not merely a teacher. She was a mathematician, a philosopher, and one of the most influential intellectual figures of her time. In the year 415 CE, she was brutally murdered by a Christian mob amid intense political and religious conflict. Her death was not literally the end of all mathematics in the ancient world, but it later became a powerful symbol of the end of an era. Over many centuries, the Greek mathematical tradition had reached extraordinary heights. Pythagorean thinkers emphasized number and proof. Plato elevated geometry. Euclid organized mathematics into a logical system, and Archimedes pushed mathematical reasoning far beyond his time. Centuries later, Hypatia became one of the most famous figures associated with preserving and teaching that tradition in Alexandria. But this center of mathematical activity would not remain unchanged forever. A major historical transformation was coming, and the story of mathematics began to shift away from the ancient Mediterranean world. Mathematics did not disappear. Its center of development moved toward other parts of the world, especially farther east. China. Mathematics for problem solving. China developed a mathematical tradition focused strongly on solving problems. While Greek mathematics often emphasized formal proof, Chinese mathematics was frequently practical, systematic, and efficient. One of the most important works that survives from ancient China is a book called The 9 Chapters on the Mathematical Art. It is a collection of hundreds of practical problems involving taxation, trade, land measurement, construction, and the payment of workers. But what makes this book especially important is the sophistication of its problem-solving methods. The Chinese method and elimination. Here is a simple example in the spirit of the problems found in this tradition. Suppose 1 plum and 3 peaches cost 15 units, while 2 plums and 1 peach cost 10 units. The goal is to find the price of each fruit. In modern notation, the equations would be x plus 3y equals 15, and 2x plus y equals 10. The Chinese method arranged coefficients systematically, often using counting rods on a counting board, and eliminated one unknown step by step. Does that remind you of anything? It is closely related to what we now call elimination. Methods in the 9 chapters are strikingly similar to the procedure later known in Europe as Gaussian elimination, even though the Chinese text existed well over 1,000 years before Gauss. The Lo Shu Magic Square. Chinese mathematicians were not interested only in practical equations. They were also fascinated by numerical patterns. One of the most famous examples is the magic square. Imagine placing the numbers 1 through 9 inside a 3 by 3 square, but not in just any arrangement. There is one condition. The sum of every row, every column, and both main diagonals must be exactly the same. In the Lo Shu square, that common sum is always 15. According to an ancient Chinese legend, a turtle emerged from the Luo River with this numerical pattern marked on its shell. The story gave the Lo Shu square a special place in Chinese culture. But it was more than a game or a decorative pattern. It reflected a deeper interest, finding hidden order among numbers. The Chinese remainder theorem. Now we come to another major idea. The Chinese remainder theorem, often abbreviated as CRT. The key idea is that a large or unknown number can be described through several smaller remainders. For a simple example, suppose we are looking for a number that leaves remainder 1 when divided by 3, remainder 2 when divided by 5, and remainder 3 when divided by 7. Numbers that leave remainder 1 when divided by 3 include 1, 4, 7, 10, 13, 16, and so on. Among these, we keep the numbers that leave remainder 2 when divided by 5. One of them is 7, and the full pattern is 7, 22, 37, 52, and so on. Each time we add 15 because 15 is 3 multiplied by 5. Finally, we select the number that leaves remainder 3 when divided by 7. The smallest positive solution is 52. This same general idea later became deeply important in modern number theory and cryptography. We can reconstruct a number from several smaller pieces of modular information. From China to India. In China, mathematics had become a powerful system for solving practical problems. But in India, the birth of a new concept of number, something different happened. India transformed the concept of number itself. Indian mathematicians developed and refined the decimal place value system, the same basic system we use today. With just the digits 1 through 9, one extraordinary symbol called 0, and the position of each digit, it became possible to write any number efficiently. Earlier systems had often used an empty position as a placeholder. The revolution of 0. But the true revolution came when 0 became a number in its own right. Why was that so important? 0 was not merely another symbol. For the first time, nothing could be represented written and used in calculation as a mathematical object. With zero and place value, even extremely large numbers could be written simply and clearly. The philosophical meaning of zero. In Indian intellectual traditions, emptiness was not always treated as mere absence. It could carry deep philosophical meaning, much like the concept of infinity. Mathematics was becoming increasingly abstract, less tied only to physical objects and more connected to mental concepts. Numbers were no longer used only for counting things. They were becoming ideas in their own right. Brahmagupta and the rules of zero. Brahmagupta was one of the first mathematicians to write systematic rules for calculating with zero. He explained, for example, that adding zero to a number leaves the number unchanged, subtracting zero leaves it unchanged, and multiplying any number by zero gives zero. He also discussed division involving zero, but this is where mathematics ran into a serious difficulty. No valid ordinary numerical rule can define a non-zero number divided by zero. Infinity and division by zero. To think about what happens near division by zero, mathematicians eventually needed more subtle ideas, including infinity and limits. Several centuries after Brahmagupta, the Indian mathematician Bhaskara II suggested that dividing a non-zero quantity by zero produced an infinite quantity. There is an intuition behind this idea. Consider dividing 1 by smaller and smaller positive numbers. 1 divided by 1/10 is 10, 1 divided by 100th is 100, and the values grow without bound. So from one side, the expression can grow toward positive infinity. But in modern mathematics, division by zero itself remains undefined, because approaching zero from different directions can produce different behavior. Negative numbers. Indian mathematicians also moved confidently into the world of negative numbers. If we subtract 4 from 3, we move below zero. Brahmagupta described positive numbers using the language of fortunes or assets, and negative numbers using the language of debts. Trigonometry, a tool for measuring the world. Trigonometry became another major part of Indian mathematics. One important motivation was the study of the sky, creating calendars, timing religious ceremonies, and predicting the motions of the sun and moon. But how can you measure the distance to a celestial object when you cannot travel to it? You measure angles from Earth and use geometry to infer distances. That creates a relationship between angles and lengths. And that is the heart of trigonometry. So, trigonometry developed partly from the need to understand the sky. Later, the same tools could be used to survey land, calculate distances, navigate, and design buildings. Indian mathematicians did not only transform numbers, they also made major contributions to the development of trigonometry. Infinite series and a major leap. Infinite series created another enormous leap. Madhava of Sangamagrama was an Indian mathematician who lived around the 14th and early 15th centuries. He explored a remarkable idea. An exact value could be approached by adding infinitely many terms. For example, an alternating series of fractions can be used to approximate pi with increasing accuracy. We discussed related ideas about infinite series in more detail in our video on the Riemann rearrangement theorem. Madhava and the Kerala school developed these ideas centuries before similar infinite series methods became famous in Europe. This changed the way mathematics could describe a solution. Earlier mathematics often focused on fixed numbers and direct answers. Now a solution could also be understood as a process, approaching a value through infinitely many stages. This idea became fundamental to calculus, mathematical analysis, and the modeling of natural phenomena. Almost anything that changes can be studied using related ideas. The motion of planets, population growth, the flow of air, and even many mathematical methods used in artificial intelligence. The real world is not always simple or perfectly exact, but mathematics allows us to approximate it with extraordinary precision. Mathematics had now become more than a collection of tools. It was becoming a complete language. But one thing was still missing. Entering Iran in the Golden Age, someone had to organize these ideas into a more unified system. And this is where our story enters Iran in the broader Islamic Golden Age, a period in which scholars from the Iranian cultural world played a central role in the development of mathematics. By this point, ideas about decimal numbers, zero, negative quantities, and infinity had grown enormously. But mathematics still needed a general language. Al-Khwarizmi and the birth of algebra for working with unknown quantities. This is where algebra enters the story. Al-Khwarizmi was one of the most important scholars of this era, born in the region of Khwarazm and working in Baghdad. He wrote a famous book known as Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala. The word al-Jabr referred to restoring or completing terms, while al-Muqabala referred to balancing or reducing corresponding terms on the two sides of an equation. You might say that earlier civilizations had already used algebraic thinking, and that is true. But earlier problems were often solved case by case. For each new question, a new solution method might be needed. Al-Khwarizmi made a fundamental change. He organized general procedures for solving entire classes of equations. Instead of solving only one particular problem, mathematics now offered methods that could be applied to many problems of the same type. This helped transform mathematics into a general language for describing unknowns and relationships. Algorithm: Al-Khwarizmi's legacy. When the works of Muhammad ibn Musa al-Khwarizmi reached Europe, his name was Latinized as algorithmi, and over time it gave rise to the word algorithm. An algorithm is a clear, step-by-step procedure for solving a problem. This simple but powerful idea is now at the heart of the digital world, from computers and programming to search engines and artificial intelligence. More complex equations with Omar Khayyam. But the story of mathematics did not end there. Some equations were much more difficult, so difficult that the earlier methods were no longer enough. One major example was the cubic equation, an equation in which the unknown can appear to the third power. Solving cubic equations remained a major challenge for centuries. Omar Khayyam approached the problem from a completely different direction. Instead of working only with numerical operations, he turned to geometry, to shapes, curves, and their intersections. Khayyam showed that certain cubic equations could be solved by constructing conic sections. The point where two curves intersect can represent a solution to the equation. This was an extremely important insight. Equations are not merely collections of numbers. Each equation can also describe a geometric object. This revealed a deep connection between algebra and geometry, an idea that later became one of the foundations of modern mathematics, where numbers, equations, and shapes are closely connected. Khayyam did not merely solve equations. He made them visible. Mathematics was moving beyond calculation and toward a deeper form of understanding. Khayyam, Poetry and Mathematics. Khayyam wrote, "The secrets of eternity neither you nor I can know. This hidden riddle neither you nor I can read." And elsewhere, in a verse traditionally attributed to him, "In this circle where our coming and going lie, no beginning and no ending can be found." But these mathematical ideas were not going to remain in the same region forever. Gradually, they found their way into Europe, and one of the people who helped popularize this knowledge there was Fibonacci. The transfer of mathematics to Europe. Through trade routes, translated books, and scholars who moved between cultures, mathematical knowledge gradually entered medieval Europe. One of the most important people associated with promoting this knowledge in Europe was Leonardo of Pisa, better known as Fibonacci. The Fibonacci sequence. Fibonacci was not merely a messenger. His work also helped make new mathematical ideas widely known. The famous Fibonacci sequence begins like this: 1, 1, 2, 3, 5, 8, 13, and so on. Each number is the sum of the two numbers before it. This sequence is not just a numerical game. Fibonacci-type patterns appear in some models of biological growth and in features such as spiral arrangements in certain plants. Popular culture often connects it to flowers, shells, and the golden ratio, although real natural patterns are more complex than a single universal formula. Competition in European mathematics. But this was only the beginning. In Renaissance Europe, mathematics gradually became a field of intense competition. Tartaglia and Cardano. Niccolò Tartaglia and Girolamo Cardano were two Italian mathematicians caught in one of the most famous mathematical rivalries in history. They were competing over one of the hardest problems of their time, solving cubic equations, problems that had challenged mathematicians for centuries. Now the cubic equation had become the center of a contest over who could solve it first. So who won? The story is complicated. Tartaglia was the first of the two to discover a method for solving an important class of cubic equations, although he did not solve every possible form. Cardano desperately wanted to know the method, so he asked Tartaglia to reveal it. Tartaglia agreed only after Cardano promised not to publish it. Years later, after learning that an earlier mathematician named Scipione del Ferro had independently discovered a related solution, Cardano published the method in his book Ars Magna. That is one reason the general solution is now often associated with Cardano's name, even though its history involves several mathematicians. The solution of cubic equations became one of the greatest mathematical advances of Renaissance Europe. Europe gets ready for a mathematical revolution. Europe now had powerful tools: algebra, the Hindu-Arabic numeral system, new methods for equations, and increasingly sophisticated ideas about infinity. The stage was set for another mathematical revolution: the development of analytic geometry, probability, and calculus. Mathematics was built by civilizations. When we look back at this entire journey, from the earliest acts of counting and the patterns of nature to the construction of the Egyptian pyramids, from Babylonian astronomical tables to Greek geometry, from zero in India to algebra in the Iranian and Islamic world, and finally to the fierce mathematical competitions of Europe, we see that mathematics was built step by step. It was not created by one person, and it did not belong to one region. It was built by civilizations. Each culture created part of the puzzle according to its own needs. The Egyptians measured land, the Babylonians calculated and predicted the sky, the Chinese developed efficient methods for solving practical problems, Indian mathematicians transformed the concept of number, and scholars of the Iranian and Islamic Golden Age developed powerful general languages and procedures for mathematics. Each civilization looked at the world from its own perspective and added something to the story. Some people searched for answers. Some searched for general methods. Others asked why those methods had to be true. Throughout history, there has also been a kind of competition over mathematics. Where did it begin? Which civilization does it belong to? Mathematics is a universal language. The honest answer is, it belongs to none of them alone. What matters is not where mathematics began. What matters is who continues its story. Mathematics is a universal language, a language humans created to understand the world. And this story is far from over.